We are going to be learning some more tests for convergence of series in this video, the comparison tests. First, let's look at a couple of sequences. A sub n equal 1 over 2 to the n plus 1, and we have the terms of this sequence plotted. B sub n equal 1 over 2 to the n, and we have those terms plotted. We can see that the terms of A sub n are always less than the terms of B sub n. Even when they get very close together, if we zoomed in, we can see that A sub n is always less than B sub n, and that is because 2 to the n is less than 2 to the n plus 1. If we add 1, of course, we get a larger number, so when we take the reciprocals, that reverses the inequality. 1 over 2 to the n is going to be greater than 1 over 2 to the n plus 1, because we know that if the denominator of the fraction is greater and the numerator is the same, that this will be the smaller fraction. So we're going to use that idea to compare the series that we're trying to test with a series that we know in this case is convergent, because our series here is a geometric series and the common ratio is 1/2, so this converges, and in fact we can find the sum. It is the first term, 1/2 over 1 minus the common ratio, which is also 1/2, so that's just 1/2 over 1/2, so this series converges to 1. Now, since we know that the terms in the series we're trying to determine convergence of are always less than this, if we summed up this series, we may not know the sum, but we would know it would need to be less than 1. So even though we don't have the sum listed here, it is a convergent series because it converges to some finite number less than 1. So this idea leads us to what is called the comparison test. Suppose we have two series with positive terms, A sub n and B sub n. If B sub n is convergent, and we know the terms of A sub n are always less than or equal to B sub n for all n, then A sub n is also convergent. It was the idea we just illustrated. If all of these terms are less than or equal to these terms, and this series converges, then the series with these terms would have to converge as well. Now there's a second piece to this. If the series B sub n is known to be divergent, and the terms of A sub n are always greater than or equal to B sub n for all n, then A sub n is also divergent. And the idea here being, if you know it is divergent and you know A sub n's terms are even greater than that, if something is the sum going to infinity, something whose terms are larger than that is going to go to infinity as well. Now, things that we'll want to compare with are things that we easily know convergence or divergence of, and P series would be great for comparisons. We know that if we have this series 1 over n to the p, that it converges if p is greater than 1. So it'll be very easy to get 1 over p to the something greater than 1 to know it converges, or if we're trying to test for divergence, we know that if p is less than or equal to 1, that this series diverges. So these would be great series to use in comparisons, to use as our B sub n's. Also, geometric series like we saw in the last example, because we easily know the convergence of those. We know that if the absolute value of the common ratio is less than 1, they will converge. We can find the sum even. And if the absolute value is greater than or equal to 1, it will diverge. So these are a couple of families of series that will be easy to use in the comparison test. So as we look here at A sub n, and the terms are 1 over n squared plus 10, we look for a known series that we could use in a comparison test. Here's these, and if we can get something that these terms are always less than or equal to, and then we know it converges, then we would know this one also converges. And so a great one to use would be 1 over n squared. Those terms are always greater than the terms in 1 over n squared plus 10, because we know that if you have the denominator become larger, the fraction becomes smaller. And so by the comparison test, we would know that since this is a convergent P series, that this is also convergent. Now let's look at another one. 1 over square root of n minus 3 are the terms in this series. And as we look at that one, they look like this. We could compare that to this series, And if we compare that to this series, because this is minus 3 here, we're taking something away from this denominator, so this denominator will be smaller than this one, and so these terms will be larger, and we can see that here. And so A sub n terms are always greater than the B sub n terms. But do we know about B sub n? Yes, we know this is a P series with P being 1/2. And so we're going to have divergence of this series. And so if this series whose terms are always less than this series diverges, then this series would also have to diverge by the comparison test. Now, as we looked at this one and we tried to find something to compare it with, we've got issues because the terms of this one are always greater because we're taking one away than this. And so even though we know this converges, if something converges and we have the terms of that thing that converges, but these terms are above those, just because this converges, I don't know what's going on above it. It could converge or it could head up, diverge, and we don't know. So the inequality is going the wrong way for using the comparison test. So sometimes we have issues with that, and we have to be careful because the terms of A sub n would need to be less than or equal to the terms of B sub n if B sub n converges, and so it's going the wrong way for that. So we are going to have another test that can help us, the limit comparison test. So we have series with positive terms A sub n and B sub n. If the limit of we take the as n goes to infinity, the terms of A sub n compared to the terms of B sub n. So we got the ratio A sub n over B sub n. If that equals L, where L is a positive finite number, so when we do the ratio of these terms, if we get a positive finite number, then either both series converge or both series diverge. Now that's going to be helpful to us. Let's look at the proof and see why this is true. So here we're going to let little m and big M be positive numbers such that this L, this positive finite number that is reached when we have this limit, is between those two. And so since A sub n over B sub n is almost L for n large, because it would be approaching L as n becomes large, there would be an integer capital N such that if we were past capital N, then we could replace that here because we had these limits on L, and we could get within however close we need to of L with this if we go out far enough. And so the ratio A sub n terms over B sub n will always be greater than M and greater than capital M if we go out far enough, if our n is greater than capital N. So then we could multiply both sides by B sub n. They were positive term sequences, so we're good to do that in inequality, and that would put the B sub n on either side, and that was provided that we're out past capital N. Okay, so now as we look at this, if B sub n converges, that was our comparison that we know the convergence of. If it converges, well then so would some finite number times this, because if it converged to something, if we multiply it by a finite number, it's still going to converge. And so therefore A sub n would converge by the comparison test, because we would have that the terms of A sub n are always less than the terms in a convergent series. Now, if the opposite is true, if B sub n diverges, so does multiplying it by a finite number. If it already is going to infinity, multiplying it by a finite number is not going to change that, and therefore A sub n diverges because we have this inequality. And so by the comparison test, if this is known to diverge and the terms of this series A sub n are always greater than that, this will also diverge. So we have the limit comparison test, and when we would want to use the limit comparison test then is when we had that issue of the inequality was going the wrong way. And so we saw here that we couldn't just use the comparison test, so let's use the limit comparison test, and we're going to compare it to 1 over 2 to the n. So let's go ahead and use this limit comparison test. So we're going to have the limit as n goes to infinity of the terms of A sub n, which is 1 over 2 to the n minus 1, and we're going to put that over A comparison series, we're going to use 1 over 2 to the n because we know that is a convergent geometric series. And when we go to simplify that, we can flip this over, and that would be 2 to the n over 1. And then as we look at that, we could express this as the limit as n goes to infinity. We could multiply numerator and denominator by 2 to the n. That would make it 1 over 1 minus 1 over 2 to the n. And then we know that as n goes to infinity, this denominator is going to go to infinity, so this fraction is going to go to 0, and we're going to get a 1 here. Because the limit of this ratio was a positive finite number, and we know that 1 over 2 to the n, our comparison series, converged, so does this series.